You don't just inherit from Web Application Factory, you inherit chaos. If you've searched for an integration testing example online, you've probably found the same one I have a dozen times. You inherit, override a couple methods, spin up a database, Bob's your uncle, you're done. It works. Well, right until someone else in your team opens that file up in 6 months and tries to figure out what order do things actually happen in. Or maybe you need to run it against SQLite or Postgres, a different database provider. Or perhaps you're staring at a DisposeAsync collision and you have no idea why these two base classes are fighting each other. So in this video, I'm going to show you a different way to set this up. One built around 4 named phases instead of that inherited chaos. Starting with your database, building your pipeline, materializing the host, and seeding your data. You'll see exactly how the Web Application Factory and Testcontainers fit together and in order they actually need to run, and why composition, not inheritance, is what makes that order something you can read instead of something that you have to guess at. And I'll show you that that same base class backing 2 completely different fixtures behind one identical contract, a nearly free SQLite file for your fast local test, and a real shared Postgres container running in Docker for all the tests that you need the real thing. And by the end, you're going to have a setup you can actually hand to someone else and expect them to understand it. A quick word from today's sponsor, AuthorizationHub. Everything we're about to build assumes that you've already got authorization logic worth testing, policies, roles, claims. AuthorizationHub is where a lot of that logic can actually live. It's a plugin for your existing ASP.NET Core web apps that's not a hosted service. You can run it, own it, and none of your data ever leaves your infrastructure. The core idea is this. AuthorizationHub takes your tenants, your groups, your roles, and turns them into identity claims as a request moves through the pipeline. Claims your authorization policies can evaluate directly. Change someone's role or group membership, and their access changes immediately. No redeploy, no code change. It uses SQL Server, Postgres, or SQLite, some of the same providers we'll be testing against in this series, and it ships with a UI, so your team can manage those users, groups, and roles without building that screen yourself. If you're managing role checks that are scattered across dozens of files, it's worth a look. AuthorizationHub.com. Now let's get into it. So why do you want to run integration tests? Well, let me start with a line that I want you to remember all the way to the very end. Bugs live at the seams. The most common place you're actually going to find a bug that takes production down is in the in-between spaces, the places where code hands off to the database, where you cross a layer boundary, where you turn an object into JSON or turn JSON into an object. And the reality is, if you're building unit tests, you're probably using mocks as a substitute for services. But a mock is an assumption about how you believe an object's going to behave. And over time, you're going to refactor those classes and their behavior is going to change. But how often do you go back and refactor that mock so that its behavior matches what it should? There's a certain amount of entropy that's just naturally going to happen when you mock behavior because a mock is an assumption. And that's why we have bugs biting us where components meet. It's the weakness of a mock. It's the assumption about how something should behave instead of how the actual behavior is written into the class. The other reason you want integration tests is for confidence. When you go to deploy, you're going to have test coverage across a large number of components in your actual HTTP pipeline. One integration test can drive real HTTP requests. It can hit the database and touch your auth. And the reality is you're going to have a whole lot less maintenance on those tests because refactors aren't going to break them as frequently. You're testing at the boundaries, not inside a specific function. And that really changes the visual picture of your test coverage. Because in the past, we thought of it as a pyramid. And at the base of that pyramid were unit tests, where we spent most of our effort. And then a smaller layer of integration tests above that. But now we've shifted, right? We've turned this into a diamond where the majority of our test coverage happens in integration tests and a smaller number of unit tests are still written, but they're focused on domain logic. And then at the top, we still have our end-to-end test using something like Playwright. So what are the scenarios that a unit test doesn't touch? Well, there's really 4 obvious ones. And the first one is middleware. Now, middleware are all the components that are inside your ASP.NET Core pipeline that process the request before the endpoints handler ever gets invoked. Things like authentication, authorization, anything like handling an anti-forgery token. And you really should have a way to test those things, but if you're just unit testing, that's not going to happen. Model binding is another great example. It's something that we take for granted because ASP.NET Core makes it so easy. You can send real JSON through the request body and it gets mapped to parameters, route values. It's the part that we take for granted, but you really should be testing it. Authorization policy. That's an area where you might have different authorization requirements that get evaluated to determine whether a user can perform some function through an endpoint. Well, it's very difficult to determine if you've actually applied an authorization policy to the endpoint, but with integration tests, it gets much, much easier. And the biggest one, well, that's persistence. In an ideal situation, you'd write an integration test that's going to go out and touch a real SQL server, a real Postgres server, a real service, as opposed to mocking it, like if you might mock a repository. And that's a huge win, and it's super important. So those are the four seams that I think you just typically don't hit with a unit test, and they're incredibly load-bearing in production. So I think it's important to talk about where we're headed. What's the actual goal? Because I think we would like to have a single test that hits a real endpoint and asserts on a real response. And we want to do that with our classic arrange, act, and assert. But our arrange, it's actually going to build a request that we can send to an HTTP pipeline through that client as an authenticated persona, as someone who's actually using your application. So when we act, we post that request to a real endpoint over real HTTP. And the assertion, obviously, is we look at the status code, or we can look at the shape of whatever the response was that was created. Everything in this talk is the machinery for making a test like this cheap and easy to write. So let's start by talking about the Web Application Factory, because it's really crucial to integration testing in .NET. It's the class that's built into the HTTP framework that spins up the HTTP pipeline that you can test against. And the key benefit here is that it boots up your real application into memory so that a test can call the endpoints over HTTP without ever actually opening a network socket. And it works by taking your application's entry point, typically program CS, your composition root, and using all of that configuration that you've already set up there. And then from that, it can generate a factory, and that factory produces an HTTP client that you can use in your test. Now, under the hood, it runs your application's real startup pipeline: dependency injection, registration, middleware, routing, authentication, endpoint mapping, that whole kit and caboodle. And the result is a fully constructed iHost running a genuine request pipeline. So from there, that factory hands you a client so you can make real HTTP calls and verify that the in-memory host returns exactly what you would expect. We really need to talk about test containers. If you're going to run integration tests against a real database, then you need a way to create that database. And often you'll see people spin up a local SQL server or a local Postgres instance to run their integration test against. But that can be a real pain because you don't always get isolation in that scenario. And just as important, if you're using a CI pipeline, which you should be, that local test database isn't going to be available in CI. And that's where test containers comes in. It's a tool that has become pretty much the de facto standard in integration testing in the .NET world. Test containers lets you take a real service and spin it up inside a Docker container. And the great part is that it has the port mapping built in, so it avoids all those conflicts if you've got multiple servers trying to use the same port in your environment. Now, the only real requirement here is that you've got a Docker API compatible runtime to create those containers in, and beyond that, it'll work with any test framework, whether that's XUnit, Inute, MS Test, whatever. But for your integration test, the workflow is to tell test containers to start up the container, run your test against it, and then tear that container down afterward so that it releases the memory and the resources that it was using. So let's take a moment. Let's set up the scenario for an integration test where we're using XUnit as our testing framework, and we'll use the Web Application Factory to set up our HTTP pipeline, and we'll use test containers to start up that instance of our database server. Now you have to pause and think about how these different pieces are actually going to work together. Because for your integration test, some of these things have to happen in a very specific order. There are interdependencies that you need to manage across their life cycles. For example, XUnit needs a host from the WebApplicationFactory, and it needs a way to start and end the test cleanly. But the WebApplicationFactory needs a database connection string from the test container to build its pipeline. That's part of the configuration step. And at some point, it actually has to start that pipeline and hand back a host. And meanwhile, the test container needs to start up the Docker container and map those ports so that it can communicate with the database server and eventually stop that container once you're done. So managing all of this can get really confusing. And I think one of the things you see with integration tests is that people don't actually think through the order in which these things need to happen in order to keep isolated, reliable tests. All right, so let's walk through an example. What I did was I created a sample application, vibe coded it using Claude. It's a really simple, minimal API that lets you get a stock price and then query back what the stock price is. And then I asked it to create an integration test for that minimal API. And this is roughly what it created. And I think it's fairly typical of the integration tests that you'll see out in the wild. And in this example that we've created, the API factory inherits from the WebApplicationFactory, and it implements the iAsync lifetime interface. The iAsync lifetime interface is what XUnit uses to manage the lifecycle of a test. And it has two methods that you have to override: InitializeAsync and DisposeAsync. InitializeAsync is the first method that XUnit calls, and it will await that function and not run the test until it's been completed. So this is a great place to start our container up with test containers. We can await that start async call, and once that's done, the WebApplicationFactory can take over. And at some point, it calls configure web host, where it can grab the connection string from the container and use it to configure the app's DB context. So far, so good. Everything actually works just fine. It does get a little bit interesting here because XUnit has its own DisposeAsync, and the WebApplicationFactory also has a DisposeAsync, and that's why you see that new keyword. It's just being hidden. So why not just inherit from the WebApplicationFactory directly? I think it's a tempting shortcut, and it's definitely the approach most examples use, but I think it creates some real problems. First, you don't have a single seam that you can await. You don't have that one function you can call, say, initialize, where once it completes, you know that the database server is set up and running, your pipeline configuration's done, your host is instantiated, and your test data is loaded and ready to go. None of that is guaranteed to be in one place. Second, the ordering of operations becomes basically invisible. You can't look at the code and know why something is happening or when without understanding XUnit's internal behavior. And let's just be honest, who's going to remember that? If you haven't touched the integration code in 6 months, you're not remembering. So there's also an issue that the create web host builder is a function on the WebApplicationFactory that just returns a plain builder. It doesn't expose any custom properties or functions that you might need for your specific integration test setup. I don't love that. And on top of it, you get collisions between create client and DisposeAsync because they have incompatible signatures across those two base classes. And you can work through those issues, but it's not something most developers are going to recognize or expect. And that's why I think it's a better idea to create a single base class for your integration test, one with a clear synchronized lifecycle. So what's that going to look like? Well, we're going to choose composition over inheritance here, and we're going to organize the setup into 4 named phases. The first phase is start database async, and its job is to make sure that the database server is set up and running inside the container. The second step is build factory. This handles configuration for the HTTP pipeline, and it's the place where we make any per test configuration changes or we swap out dependency injection registrations. maybe a mock time provider or some service that we need to mock so that we can control the test behavior. The third one is MaterializeHost. And the purpose of this function is simple. By the end of it, we want to know that a fully instantiated pipeline has been created and will return a host that we can interact with. Finally, we have seed async, and this opens up a single scope and seeds the database with whatever test data we need. Now, this base class becomes the common setup for our integration test. You might inherit from it, but any inheritance is really just a way to specify what kind of database container you're using, like SQLite or Postgres. The base class itself stays common across all those different container types. All right, so let's just take a second to talk about that database access, because how do you design a base class that can be used by every database provider? Well, I think the rule is fairly simple. For every member, just ask yourself the question of, is there a default answer that's actually right? Or is it going to be a trap? Would I forget to override it? If there's no safe default, that means it should be abstract. For example, starting a database async is going to be different for Postgres versus for SQLite. In one case, you're starting a container, and the other, you're not really doing anything. And so those answers are just worlds apart. The same scenario for stopping the database async or configuring a database services or getting connection string. Those are all going to be different by database provider. Now, other things like populate DB async is going to be a function that puts rows of data in the database, and that's going to be common regardless of the database provider. So we'd want to put that in the base class. So let's just look at an example of a fixture that inherits from that base class. And I think SQLite is a great one to start with because there's not so much to it. You don't need a test container to spin up in Docker at all. It's really just a file. So start database async can just return a completed task because there's nothing to start. Now there is an interesting detail with the connection string. We're going to set pooling equal to false because that helps us tear down and delete the file cleanly at the end of the test. And that file name itself, well, that becomes our isolation mechanism. We can just change the file name with each test run so that it gets its own database. And because it's a GUID, we're not going to get collisions. So it really ends up being the cheapest fixture in our test suite while we're still using the same contract that we would use for Postgres. So now let's go to the other end of the spectrum and talk about Postgres. Starting up a Postgres server costs real seconds, and the reality is you only need to do that once for the entire test run because you can get isolation at the database level instead of the server level. And that's why we use a lazy task here. The first fixture that asks for that Docker container to be set up triggers the start async, and every other fixture just awaits that same task. So inside that shared container, each fixture gets its own uniquely named database, and that's a far cheaper layer of isolation to build on top of a more expensive shared resource. Now get connection string needs that container's live address, which is exactly why it has to be a method and not a property, and the teardown gets deferred but not skipped. Testcontainers resource reaper tears down the whole container when the process exits. And the takeaway is that two fixtures making completely opposite resource decisions, one cheap and disposable, one shared and expensive, can live behind the exact same abstract contract. So that's the first step, starting up the database server. Now let's talk about the second step called build factory. The idea here is that we want an opportunity to load per fixture configuration settings, meaning for each individual test, we might need configuration specific to that test, and we want a place to set that up for our HTTP pipeline. And we also want to register a real database connection and probably maybe a time provider, because that's a fairly common pain point in integration test. But we want to do this while we're still using our real program CS file to build that pipeline, the same composition route that your production system actually uses. So build factory will write out the connection string using a known key, which the database service can configure and then can read from. And the important thing to remember here is that build factory is writing the recipe. It's a recipe. The callback it registers doesn't actually fire until the host is materialized later. Which brings us to step 3, MaterializeHost. The third step in this process is MaterializeHost, and it's that phase where we take the blueprint for the HTTP pipeline and we turn it into a real pipeline and we return the host. Now, going back to that original example code, one of the problems was that you never really knew when the actual pipeline got created. It actually turns out that it happens at the moment someone touches the service property on the WebApplicationFactory. And as soon as that property gets accessed, it triggers the pipeline to actually get built. Who knows this stuff? That's exactly what MaterializeHost does. It touches the services property, which returns a host that we can later use as part of our seeding process. But the real value here isn't in the mechanism itself, it's that we've taken a single, easy to miss property access and we've promoted it to a named method that we can say precisely and explicitly when that pipeline will get created. All right, now we're on to the last step of our 4, which is called seed async. And its goal is to separate the plumbing from the payload. So seed async owns the scope and populate DB async owns the rows. So we need that DB context to be scoped because if we were to resolve it from the root provider, we would be creating a captive dependency problem and one that could lead to some bad or leaked test data. So what seed async actually does is it opens a new scope and uses that scope to create the schema for the database. The actual row level work happens inside populate DB async, and as I mentioned, that function is common across all the database providers so that any rows we need to create for our integration test live in that function in the base class. So that's it. That's how we manage the lifecycle of our integration test. Everything in this section boils down to one method with 4 phases, each a named step depending on the last. In this scenario, we use composition for what we can borrow. We hold the factory as a field. We don't inherit from it. Inheritance still has a role, but it's reserved for database access where we need behavior that's specific to a given database provider. And the result is that timing becomes a feature and not an accident. MaterializeHost makes that ordering explicit. You know exactly when the pipeline comes to life instead of it happening somewhere in the XUnit machinery. Now we've covered a lot of material, and I know it isn't the easiest to absorb in one pass, but I think this will give you a different way to think about setting up your integration test. One that makes it much clearer what's happening and when it's happening. Now, the next time you have to go back and touch that setup and refactor it to do something different, it'll be easier to understand. And that's really the value of this exercise, making integration tests that are more readable, understandable, and easier to trust. Thanks for listening.